So today I want to talk about two things. I want to talk about damping, and it's not the same word as dampening, because dampening is not a physics concept. It's when you walk out in the dew and your socks get wet. We're talking about damping, which is when energy leaves a system that's oscillating. So if I've got a pendulum, imagine I've got this pendulum bob right here, and it's swinging. So it's going to go to over here a moment later, and then it'll go back to here and back to there. And I could graph this, we'll call that x, as a function of time. Oh, look how I've started myself negatively. Shucks. Would you believe that x will begin, let's say x begins at negative a, and then does this? Would you believe that this won't go on forever? In fact, it will gradually approach an energy of 0, or gradually approach a final amplitude of 0. We can define A at the beginning to be the amplitude, but notice that this is gradually decreasing. That's damping. And that's the fact that, well, gradually energy is leaving the system because of friction, and usually we say that that force of damping is a force of friction. And well, I guess, ooh, this is interesting. The force of damping doesn't depend on position. When do you think the greatest damping is happening for a mass on a pendulum, or for that matter, a mass on a spring? When do you think it's greatest slowed down? Probably not when it's up at the top or down at the bottom. I don't really see how friction can act on it at all when it's at rest. So it's probably going to depend on how fast we're going. But is the damping force, which does definitely seem to be a friction force, is it in the direction of the velocity? Nope, it's the other way. And what about how big it is? Well, we can just lump that into variable b. As we've seen in a dropping coffee filters lab, we know that sometimes there's this other frictional force on something that's moving very fast. We might have b times v to the n, where n is about 2 or so for fast things. It turns out that there are even small terms of v to the third and v to the fourth that happen if you start going really, really fast. The damping force from the wind becomes stronger and stronger and stronger. This is very obvious because if you stick your hand outside of a car and you're going 10 miles an hour, then you don't really notice much going through your fingers. But if you're going 60, your hand's significantly pushed back. Sure. So what we know about damping is there are kind of 3 classes of damping. And the 3 classes of damping are, well, they're underdamped, overdamped, and critically damped. And that is, well, this is like Papa Bear, and this is like Mama Bear, and this is like Baby Bear. Just right. Let's see. Critically damped. And I want to talk about these 3 types of damping with examples. So in this system that I just showed you, where I'm going to zoom out from it a little bit, but underdamped looks like this. This is time, and this is the position of my oscillator. If I've got something that's underdamped, it means I'm taking a little bit of energy away from it each cycle. And it's doing something like this then. And we could talk about the envelope. This is called the envelope of the decay here. Do you recognize this kind of a function? It starts from a particular value and it gets smaller and smaller and smaller very gradually. I guess it gets smallest most rapidly early on, but it changes less as we go further on. Yeah, yep, that's an exponential. So we could talk about the amplitude as a function of time. the amplitude as a function of time, not the position as a function of time, but the amplitude itself is actually decreasing. That amplitude is the initial amplitude, we could call it A naught or something, and then we'll multiply that by this decaying exponential. So it's got to have, well, it's got to have a minus sign up here, and calculus can show you this very obviously, very easily why it is. It's negative b over 2 times the mass of the system times t. And the cool thing about this is this stuff that's in the exponent has units that aren't units. Well, it doesn't have units. So this is an expression for how amplitude decays. So let's look at this b right here. That's from the force of damping. It's b times the speed of the system. So if you'll consider this, if b is bigger, we've got a greater damping force. And that makes sense, because in the exponent, it's going to get bigger faster. Now, if the exponent of e gets bigger, well, more negative, faster, then that means that this sucker is going to be damping like that. Yeah, okay. So maybe it's a good time to talk about critically damped. Let's see if I can make some boundaries between these guys for you. Critically damped systems get, where am I? Blue? Okay. Critically damped systems get smaller much, much faster than that. To use the same scale, I'm going to have it, ooh, watch this. I'm going to have it go like this. And it's gone. All the energy is gone before first oscillation. Notice that it wouldn't even be possible to say that this oscillated because it never quite reaches. If I put this in pink for you, that makes a little bit more sense. It never quite reaches 0. It approaches 0 closer and closer the whole time, but it never quite gets home. This would be like using a pendulum and having it go in like maple syrup or something. Can you imagine a pendulum in maple syrup that would go and never quite make it back? All right, and the other idea I want to discuss is overdamping, and that seems to be like there's too much friction. How can you have too much friction? This was always a surprise to me. Every time I studied this, it was like, what? Too much friction? Too much friction to safely get the energy out? It seems to me like the more friction you have in a system, the faster the energy will leave the system. All the time, right? But until you start to draw this graph, then you begin to believe me. Check this out. If we've got too much friction, it's like trying to make a pendulum go through wet concrete. It would be like, it'd be extremely slow. And so we're talking about something like this, where it's still exponential and it's still approaching an amplitude of 0, but, well, still we have no oscillations. So I'm going to write that down. No oscillations, but long time to relax. So that's the difference between critically damped and an overdamped system. And you can imagine, here, should I tell you about this yet? No, but let me just say that all the energy is gone before the first oscillation, and this is the fastest way. It's the fastest way to return to equilibrium. The fastest way to return to equilibrium is by critical damping. Now, overdamping does return to equilibrium, of course, with infinite time. We'll get exactly there, but over some finite amount of time, it gets really close to equilibrium, so much so that you could say it's relaxed. But overdamping takes too long. Can you think of a system where you want it to return to equilibrium as soon as possible? I can think of several, but one of them is this one. When my car hits a pothole, I want it to bounce, but gradually. Imagine going in a car that's got busted shocks. That sucker is going to bounce and bounce and bounce and bounce and bounce and bounce and bounce, and that's going to be annoying, right? Is that overdamped or underdamped? What's the problem with the car with the bouncy shocks? You got it? Do you have it? Do you know?
I would think that it would be... Wait.
It's underdamped. The car with bouncy shocks is underdamped because that sucker keeps bouncing for too long. Now, what is the problem with the car that's overdamped? Oh, shoot. Well, that's almost like having no springs at all. That would mean you hit a pothole and boom, you've got to deal with it because you're going to be moved out of the original position of your seat for a long time. That feels too tight on your shocks. So this is too springy and this is too tight. We want critically damped to get the energy from the pothole out of our system as quickly as possible. So there are cars that have tunable shocks. Awesome. Some cars tune their shock absorbers so that you can always achieve that. I think it's I before E, even in achieve. There we go. Maybe it's not. Correct me if I'm wrong. All right. The amplitude, but notice that this is gradually decreasing. That's damping. And that's the fact that, well, gradually energy is leaving the system because of friction, and usually we say that that force of damping is a force. And does this, would you believe that this won't go on forever? In fact, it will gradually approach an energy of zero, or gradually approach a final amplitude of zero. We can define A at the beginning to be back to there, and I could graph this, we'll call that X, as a function of time. Oh, look how I've started myself negatively. Shucks. Would you believe that X will begin, let's say X begins at negative A, and then when your socks get wet. We're talking about damping, which is when energy leaves a system that's oscillating. So if I've got a pendulum, imagine I've got this pendulum bob right here, and it's swinging. So it's going to go to over here a moment later, and then it'll go back to here. So today I want to talk about two things. I want to talk about damping, and it's not the same word as dampening, because dampening is not a physics concept. It's when you walk out in the